So the deflection is due to a repulsive force showing that a positive charge is present in the atom, which is called as the nucleus. The nucleus is surrounded by electrons that move around the nucleus in a circular path called orbits. The volume occupied by your nucleus will be very, very small compared to the size of your atom. So atomic number is equal to your number of protons, and in an electrically neutral atom, it will be also equal to your number of electrons. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So today we are beginning with the session 2 of our chapter, Structure of Atom. Yes, so in last class we discussed about a basic introduction about how the subatomic particles were discovered. Then in detail we discussed about the discovery of our proton, electron and neutron. Yes, so in today's class we will be discussing about atomic models, under which you will be studying Thomson's model of atom, Rutherford's alpha ray scattering experiment and Rutherford's atomic model. Okay, and then we'll be discussing about isotopes and isobars. Yes, so let's begin with the first topic for today, that is atomic models. Yes, so in last session we discussed about how the subatomic particles were discovered, right? The electrons, protons and neutrons. But we did not get any idea regarding how the electrons are distributed or how the electrons, protons and neutrons are distributed inside the atom. Like where exactly are the electrons, protons and neutrons present inside the atom? Yes, so different scientists proposed different atomic models to understand the distribution of the subatomic particles inside the atom. Yes, so we will be studying in this chapter about different atomic models that were proposed to explain the distribution of these charged particles in an atom. So in the chapter you will be seeing Thomson's model of atom, Rutherford's nuclear model of atom, then comes Bohr's model of atom and then quantum mechanical model of atom. So in this session we will be discussing only the first two. Right, so let's begin with the first one, that is Thomson model of atom. So as the name suggests, you can understand who proposed this model. Yes, it is Thomson. J.J. Thomson proposed the model in the year 1898. So what is the speciality about this model? What is Thomson model about? Yes, so what he considered is, according to his model of atom is considered as a positively charged sphere of radius 10 to the power minus 10 meter, in which negatively charged electrons are embedded. So as you can see here, Thomson considered atom as a positively charged sphere. You can see here, it is a positively charged sphere in which your electrons or negatively charged particles are embedded. See, you can see the negatively charged particles here, right? So the whole of the sphere is positively charged and your negatively charged electrons will be embedded in it, right? And the mass of atom is considered to be evenly distributed over the atom. So the mass of the atom is distributed all over the sphere. But as of now, we know that the mass of the atom is concentrated in the nucleus, right? But according to Thomson's model of atom, the mass of the atom is evenly distributed throughout the sphere. Yes. Now, it is also called as plum pudding model, raisin pudding model or watermelon model. Why is it called so? So you can compare the model of atom proposed by Thomson to a watermelon. See, the red color part you can see here, yes, of the watermelon, that is considered as the positively charged sphere. Yes, and the seeds of this, yes, the black color seeds you can see, yes, that are considered as the electrons, the negatively charged electrons, right? So you are able to relate it. Hence the name watermelon model, or you can also call it as plum pudding model or raisin pudding model. Clear? So the Thomson's model of atom was able to explain the neutrality of the atom. That means we understood that there are positively charged particles and negatively charged particles. So they neutralize with each other. We know that atom is supposed to be electrically neutral, right? So the positive and negative charges cancel out each other, and he was able to explain the neutrality of the atom. but he could not explain the results of alpha scattering experiments, and he was not able to explain the stability of the atom. So after Thomson proposed his model of atom, Rutherford conducted alpha ray scattering experiments. So the results that he obtained from there was not able to be applicable in this Thomson model of atom. So it couldn't explain the results of alpha ray scattering experiment. He was also not able to explain the stability of the atom, right? But he was able to explain the neutrality of atom. Yes, I hope Thomson model of atom is clear. It has its own limitations. So this is not the accepted model of atom. Then came Rutherford's alpha ray scattering experiment that we will be discussing now. So after Thomson proposed his model of atom, Rutherford did experiment which was called as alpha ray experiments, and he was able to propose Rutherford's nuclear model of atom. So before that, you need to understand what was the experiment that he did which led to the Rutherford's nuclear model of atom. So we'll be discussing about Rutherford's alpha ray scattering experiment. Right. So what he did is he bombarded thin foils of metal like gold with fast moving alpha particles. Right. So what exactly is alpha particles? It is helium-2 plus ions. Right. Yeah. So bombarded thin foils of metals like gold with fast moving alpha particles. And the gold foil is surrounded by zinc sulfide screen. Yes, we studied this in last session also. Yes, it's a fluorescent material, right? Which produces a tiny flash when the particles struck on the screen. So you can see the diagram here. So what is happening? From a source, alpha particles are being directed to your thin sheet of gold. You can see here. So what happens here? Once it reaches the gold foil, the alpha particles will deviate in random directions, right? So when the alpha particles deviates and touches the zinc sulfide screen, a tiny flash will be produced. You can see a spark there, as you can see in the picture which is given here. So I hope you understood. From a source, alpha particles or your helium-2 plus ions are directed towards the thin sheet of gold foil. Yes, and it is surrounded by a zinc sulfide screen, which is a fluorescent material. So if any particles come and struck there, it will produce a tiny flash, or you can see a spark there, right? So these sparks were seen, right? This was the experiment that he did. So what were the observations that he was able to make from this particular experiment? See, most of the alpha particles passed through the foil without having any deviations. So as I said, once the alpha particles touches the gold foil, it starts deviating, right? So what he was able to observe that most of the alpha particles did not show any deviations. That is, most of the alpha particles passed through the foil without showing any deviations. So they passed through the gold foil without showing any deviations. That is, in the same path, right? Now, few of the alpha particles underwent deflections through small angles. And the third one was very few of the alpha particles deflected back through an angle of nearly 180 degree. Yes, if it went this way, exactly the same way, it returned back, deviated back. So these were the observations that he was able to obtain from his experiment. That is, most of the alpha particles passed through the gold foil without any deviation. A few of them deviated at small angles, and a very few of them deviated back exactly at 180 degree, right? So from this observation, he was able to make his conclusions, right? So let's see. Most of the space in the atom is empty, as most of the alpha particles pass through the foil without any deviation. So what was the first observation? Most of the alpha particles passed through the gold foil without any deviation, right? So what was he able to conclude from that? Most of the space inside the atom is empty. So as you can see here, most of the alpha particles are passing through the gold foil without any deviation, right? You can see here, there are no deviations that can be observed. So he was able to conclude that most of the space inside your atom is empty. Right. Now the second one, a small fraction of alpha particles deflected at small angles. So the deflection is due to a repulsive force showing that a positive charge is present in the atom, which is called as the nucleus. Right. So we know that the alpha particle that we are directing towards the gold foil is positively charged, right? So If the alpha particle is showing deviation, that means there must be some positively charged particle which is present inside your atom, right? So that is what is written here. A very small fraction of it is deviating it in small angles because they are coming close to some repulsive force that is happening. That is, a positive charge is present somewhere inside the atom, so that once your alpha particles reaches close to it, it starts deviating from there, right? You know positive charges repulse, right? So a repulsive force will act and your alpha particles will start deviating in small angles. So that positively charged area is called as your nucleus, right? Yes. Now the third one, since very few alpha particles deflected at small angles, the volume occupied by the nucleus is very small compared to the total volume of the atom. Yes, from the experiment, he was able to observe that only very few of the alpha particles deflected back at exactly 180 degree. Yes, you can see that only few of it is deflecting exactly backwards, right, at 180 degree. That is because the volume of the positive charge, yes, we understood that there is a positively charged nucleus there. The volume occupied by the nucleus inside your atom is very, very small compared to the whole size of your atom. Yes, that is why only few of them is deviating at 180 degree. So the radius of atom is about 10 raised to minus 10 meter. If the radius is around 10 raised to minus 10 meter of the atom, your nucleus will be only having a radius of 10 raised to minus 15 meter. So the volume occupied by your nucleus will be very, very small compared to the size of your atom. Yes, so these were the conclusions that he made from his experiment. Right? So from the observations and conclusions that he made from his experiment, he was able to propose his Rutherford's atomic model. So let's see what is Rutherford's atomic model. What did he propose in it? Yes, so the positive charge and most of the mass of the atom is concentrated in an extremely small region which is called as nucleus by Rutherford. So the name nucleus was given by Rutherford. So what did he say? The positive charge and most of the atom is present inside a very small region which is called as the nucleus. You can see here in an atom, yes, the positively charged nucleus occupies a very, very small region, right? Yes. So what about Thomson's model of atom? He considered that the positive charge is spread throughout your atom, right? But Rutherford was able to tell that, yes, the positive charge only existed in a very small region, right? Which is called as your nucleus. And the nucleus is surrounded by electrons that move around the nucleus in a circular path called orbits. Right? So the nucleus is present and around which your electrons will revolve around in circular paths which is called as orbits. Yes, you can see here, right? Now, electrons in the nucleus are held together by electrostatic force of attraction. So we know that your nucleus is positively charged and your electrons are negatively charged. So there will be an electrostatic force of attraction between them. So they will be held in their places. Right? So this is Rutherford's nuclear model of atom. So now Rutherford's nuclear model of atom also had its own limitation. Even this is not the one which is the accepted model of atom, right? So let's see. The stability of the atoms couldn't be explained by Rutherford's atomic model. So what did we study? There will be a positively charged nucleus and the electrons will be revolving around the nucleus in circular paths which is called as orbits. So we know that when the electrons is moving in circular path, it means that they are accelerating, right? So according to Maxwell, what we have studied, when a negatively charged or any charged particle is accelerating, they have to emit radiations or they will emit radiations, right? So these electrons are negatively charged particles. They are accelerating, right? So they will emit radiations. So when they are emitting radiations means they will lose their energy. So what happens? They lose energy and eventually they have to fall inside your nucleus. But this is not happening. So he wasn't able to explain this phenomena that is supposed to happen because according to Maxwell, when electrons are revolving, that is accelerating, they need to emit radiations by which they will lose their energy and eventually fall inside the nucleus. But this is not happening. Yes, this wasn't being able to explain by the Rutherford's model. Now, he was also not able to explain continuous spectrum is expected, but in reality, a line spectrum is obtained. and he did not give any idea about the distribution of electrons in the nucleus. So these were the limitations of Rutherford's nuclear model of atom. So now let's move on to the next topic, that is representation of atom of an element. So how you can represent an element, we are going to study now. So before that, you need to be knowing these two terms, that is atomic number and mass number. So what is atomic number and mass number? So atomic number is equal to the number of protons present in the nucleus of an atom, and if the atom is electrically neutral, that means if it is not existing as ions, that is if they are having no charge, that is electrically neutral, then it is also equal to the number of electrons. So what is atomic number, which is represented by the symbol Z? Okay, so atomic number is equal to your number of protons, and in an electrically neutral atom, it will be also equal to your number of electrons. Now the second term is mass number, which is represented by the letter capital A. Now that is equal to the number of protons plus number of neutrons. So protons and neutrons are present inside your nucleus, right? So we studied that the mass of the atom is mainly due to the mass of nucleus, right? So it is equal to number of protons plus number of neutrons, and protons and neutrons together can be called as nucleons. Yes, present inside the nucleus, hence it is called as nucleons. So instead of writing like this, you can also write it is equal to the number of nucleons. So you can see here, this is how you have to represent your element. Yes, this X represent the element, whichever element you are wanting to represent, the symbol of that element you have to use in the place of X. Then what is A? A is your mass number and Z is your atomic number, right? So don't get confused. A means usually you will think it will be atomic number. No, it is in the opposite way. Yes, Z is your atomic number and A is your mass number. Yes, clear. So we can take an example here. Lithium. You know that the atomic number of lithium is 3, right? And the mass number is 7. So this is how you represent this element. The symbol of lithium is Li, then you write the atomic number here and the mass number in here. Yes, you can also see the example of helium here. Yes, the atomic number of helium is 2 and the mass number is 4. Yes, I hope you understood how you can represent the elements. Right. So now let's quickly do a numerical based on this. Right. So how many neutrons, protons and electrons are there in the following nuclei? Yes. So the representation of the element is given. So from here, you know that this is the atomic number and this will be your mass number, right? So atomic number is equal to 26. So what does that mean? Yes, the number of protons is 26, right? And it is an electrically neutral atom. Are you able to see any ions there? No, right? It is an electrically neutral atom. So this will be also equal to your number of electrons, right? So now what we have to find? There is one more thing to find, number of neutrons. So mass number is given here as 56. Yes, which is equal to your number of protons plus number of your neutrons, right? So if I take the difference of it, that is A minus Z, if I do, what will we get? Number of protons plus number of neutrons minus number of protons. Yes, so that will basically give me the number of neutrons. Yes or no? So if the question asks you to find number of neutrons, you just have to take the difference of your mass number and atomic number, which will directly give you the number of neutrons. So the number of neutrons in this case is what? It is 56 minus 26, that is 30. Yes, so we calculated the number of protons, which is 26, which is equal to number of electrons, and your number of neutrons is 30. Right? So the next element, which is given magnesium, yes, atomic number is 12 and mass number is given as 24. Yes, so what will be your number of protons? Yes, it is equal to your atomic number, right? So that will be equal to 12. And what will be your number of electrons? Yes, it is atomic number itself because it is an electrically neutral element. Yes, atom, electrically neutral atom is given here. Yes, and your number of neutrons. What it will be? How you can calculate your number of neutrons? It is just 24 minus 12, which will give you again 12. Yes, I hope this is clear. Now moving on to the next one, write the complete symbol for the atom with the given atomic number and mass number. So this is a different type of question. Mass number and atomic number is given here. You have to represent your element. Yes, how do we represent the element? In this form, you have to represent it. Yes, so the atomic number is given as 17. You know which element corresponds to the atomic number 17? It is chlorine, right? So the symbol is Cl. Now atomic number is given here, mass number is given here, that you have to write on the top. Yes, so as simple as that. So now let's see our last question. The number of electrons, protons and neutrons in a species are equal to 18, 16 and 16 respectively. Assign the correct symbol to the species. So in this case, the number of neutrons, electrons and protons are already given. Now you have to calculate your atomic number and mass number and represent it in this form. Okay, yes. So the number of protons is given as 16. The number of neutrons is also given as 16 and your number of electrons is 18, right? So the number of protons is given as 16 means that will be your atomic number, right? So we know that the element which is having atomic number 16 is sulfur. Yes, so you write your atomic number here. Now how can you calculate your mass number? That will be equal to number of your protons plus number of neutrons, right? That is 16 plus 16 which will give you 32, right? Okay, so we have our number of protons and number of neutrons. We used it, we calculated our atomic number and mass number. So now you can see that the number of electrons is 18, right? If it was an electrically neutral atom, that is the number of electrons must be equal to your number of protons, right? So this indicates that your element or your atom is not electrically neutral, right? So it is having 2 extra electrons. Yes, so what will the charge be here? It is 2 minus, right? So this will be added on to your number of electrons. Yes, so now in total what will be the number of electrons? It is 16 plus this 2 will come. Yes, 2 minus charge is written because there is 2 extra electrons that is present, right? So that is 2 minus charge. Yes, I hope that is clear. So we were able to understand it because the number of electrons here is 18 and the number of protons is 16. So it is not equal, right? 2 extra is there, right? So that is written as your 2 minus. So I hope this is clear. Now let's move on to our next topic, that is isotopes. Yes, we'll be studying about isotopes and isobars. First, let's begin with isotopes. So what are isotopes? They are atoms of same element with same atomic number but different mass number. Yes, they are atoms of same element. The mass number will be different, but their atomic number will be same. Yes, so as you can see here, protium, deuterium, tritium. You are familiar with this. These three are the 3 isotopes of your hydrogen atom, right? So as you can see here, here also it is 1, here also and here also. Yes, the atomic number is same for all these 3. And the mass number is differing. Here it is 1, here it is 2 and here it is 3. Right? So you can remember it in this way. Isotope. You can see here a top word is there. So you can remember it as the top part, whatever is present on the top will change. Yes, present on the bottom will remain the same. So that is how you can remember your isotopes. Okay. So H11, H12 and H13. This is an example for your isotope. You can take it in the case of carbon as well. Carbon is also having 3 isotopes. Carbon 12, carbon 13, carbon 14. You can see here the atomic number is the same and it is the atoms of your same element, that is carbon, right? The mass number is changing. It is 12, 13 and 14, right? And in the case of chlorine also you can see atomic number is same. Your mass number is changing, 35 and 37. So the nuclei of isotopes have same number of protons but different number of neutrons. So what exactly is changing here? The atomic number in all these cases same, right? But the mass number is changing. So basically the number of neutrons is changing in these cases, in the case of isotopes. Since the chemical properties are determined by the number of protons and electrons, different isotopes of elements have similar chemical properties. So we know that in chemical reactions, electrons are the ones which takes place in chemical reactions, right? So in the case of isotopes, the number of protons and number of electrons are the same. Yes, even if the mass number is changing, the number of protons remains the same. Number of protons and number of electrons remains the same. That means they will have the same chemical properties, right? Yes. Now moving on to isobars. Now these are atoms of different elements. Okay, they are atoms of different elements with same mass number but different atomic number. So different atomic number means it is supposed to be 2 different atoms, right? So they are atoms of different elements with same mass number but different atomic number. Exactly opposite that of isotopes. In the isotopes case, the mass number is changing, atomic number remains constant. Here, the mass number is constant and the atomic number changes. So, you can see the example that is given here. See, the mass number in this case is 40. Here also it is 40. Here also it is 40. But the atoms of your elements are different. This is argon. Here it is potassium and here it is calcium, right? And the atomic number is changing. Clear? Yes. There is two more things that you have to remember, that is isotones and isoelectric species. So what is isotones? So they are atoms of different elements having same number of neutrons. Okay. So when you subtract your mass number and atomic number, you get the number of neutrons. Yes, so they are atoms of different elements which will have the same number of neutrons. And what is isoelectronic species? So as you can see from the name, iso, same, electronic species, they will have the same number of electrons, right? They are atoms having same number of electrons. So isotopes are atoms of same element. Yes, they are atoms of same element having same atomic number but different mass number. The top part will change. Remember it like that. And isobars are atoms of different element having same mass number and different atomic number. Isotones have same number of neutrons and isoelectronic species have same number of electrons. I hope it is clear. So in the next session, we will be discussing on the developments leading to the Bohr model of atom, the electromagnetic waves and the wave theory, characteristics of wave electromagnetic spectrum. So that's all for today. Thank you.